I'm happy to introduce you today to Jonathan Samir Matthis. Known John for a long time. We shared an office together as graduate students at RPI, where he was a graduate student from 2008 till 2014, where he earned his degree in cognitive science. We both worked in the laboratory of Dr. Brent Fajan. Great to get to know John while I was there. We worked on very different topics. John, even at the time, really just the very first project he worked on really was on walking. He's been just continuing down that path since then. But now he's got, let's see, a few publications under, one from Royal Society, one just accepted PNAS, one currently under consideration at Nature. Good luck. Really great. So John's really, at a young age, he's still a postdoc. Now he's, since at 2014, he moved on to UT Austin, where he took a position working in the laboratory of Dr. Mary Hayhoe and working with Dana Ballard, the shared laboratory. So even as a postdoc, John's already made a really considerable impact in the field of understanding how vision plays a role in guiding walking behavior. We're all very lucky to have him here today. Very happy he's been able to join us. Thanks for coming, John. Great. Usually we do the end of the talk. Everybody, John Matthis.
So, hi. Thanks for having me up. Thank you, Gabe. And thanks for showing up. So like Gabe said, my main interests are related to the visual control of locomotion, and specifically the visual control of foot placement when you walk over rough terrain. And it's worth talking in an environment like this, and also just in general, about why this is an interesting thing to study and why studying specifically the visual control of walking is something that is an interesting and worthwhile pursuit, and why it might be of interest to people who have a more engineering-minded focus on things like imaging in general. So walking has a sort of special place in the nature of in sort of the history of humanity, right? Our definition of our evolutionary line begins with our adaptation towards bipedal locomotion. That's when we diverged from the apes, is when we started to stand upright and adapt for efficient long-range locomotion. Although there's a bunch of advantages to being a biped, not the least of which is it gives you hands, which you can adapt for non-locomotor purposes, which is a unique thing in the animal kingdom. And it also is exceptionally energetically efficient. Bipedal walking is particularly unstable. So when a bipedal walker puts their foot on the ground, they need to commit their entire momentum of their body to that planted foot. And so it's imperative that a walker gather the information that's necessary to place their foot in a location that will be capable of supporting their body weight and facilitate the transition of momentum from one step to another. So for humans, being the visual creatures that we are, that puts a lot of effort, effort onto our visual system to be able to gather the information necessary to guide foot placement. And so one of the things that I've been studying, and one of the sort of overarching themes of this kind of research, is to understand how the sort of physical dynamics and sort of the biomechanics of walking shapes the way that we use visual information and the way that our visual system and our locomotor system sort of work together. So one of the aspects I mentioned is that bipedal walking is exceptionally energetically efficient. And one of the ways that we maintain that level of efficiency is to basically exploit as much of the physics of our bodies as we can as we move through the world. So basically minimize the amount of effort that we have to put through our muscles and maximize the amount of energy that we get for free from the sort of physical dynamics of our bodies. So this is what's called a passive dynamic walker. It's a sort of particular type of robot which really exemplifies the ability to exploit physical dynamics. So this mechanism, if you want to call it a robot, it's up to you, has no motors or no actuators, no sensors, nothing whatsoever in it. And yet, because of it, the way that it's shaped, is capable of generating this sort of remarkably human-like gait when walking down a shallow slope. And basically, the idea is that in the same way that that the physical structure of this robot facilitates this sort of bipedal gait cycle, humans are similarly very good at exploiting our physical dynamics in order to move with a tremendous amount of efficiency and minimize the amount that we have to use our muscles to move our body through the world. Because using muscles is expensive and physics comes for free. So a large part of my dissertation and sort of my earlier work on the study of walking was meant to look at the ways that this sort of exploitation of physical dynamics shapes the way that we use visual information to guide foot placement in environments where the ground is complex enough that we actually need to adjust our foot placement appropriately for upcoming terrain. So in service of that goal, I built a system, actually sort of an early version of the kind of ground plane terrain system that Gabe built for his lab. And this system uses a projector pointed at the ground, which gets synchronized to a motion capture system, so that when the subject moves through the world and steps on virtual obstacles, the system will recognize those collisions and keep track of them and log them as collisions. So then I'm going to sort of simplify the story tremendously, but one of the early experiments there, subjects would simply walk from one end of the room to the other while avoiding stepping on any of these sort of simulated obstacles, which is something that people are quite good at. So using the system, so the software knows where the person is, and so then you can basically manipulate how far ahead subjects can see terrain as they walk over this environment. So basically, as you're walking, your ability to plan ahead is limited by the fact that the targets are only drawn when you get within a certain distance of them. So then the question becomes, how far ahead do you need to see before you start seeing, before you can walk at the same level of performance that you can if you have unconstrained vision? So again, simplifying the story a lot, one manipulation would be what happens as you start to constrain that visibility window and sort of limit how far ahead subjects can see. And one of the most immediate results that pops out of that is that you get a relatively flat response when you sort of constrain steps, sort of 5 steps out, 4 steps out, 3 steps out. But you see this rapid sort of degradation in stepping accuracy when you constrain steps to about 2.5 steps ahead. So this shows that when people can't see 2 or more steps ahead, they start to collide with those obstacles a lot more. There's a bunch of other metrics that I'm not going to talk about, showing that basically walk performance degrades dramatically when you limit the ability to see, when subjects cannot see at least 2 steps ahead as they're walking over sort of complex terrain. So the result of all these sort of series of studies winds up showing that there's actually a relatively narrow window within the gait cycle where subjects need to have visual information about the upcoming terrain in order to support accurate walking behavior. So for example, when you're walking through the world, you really only need to see the terrain relevant to this step by this point, which is about 2 step lengths ahead. But then you don't need to see it sort of after the foot leaves the ground. In the study shown here, basically presenting targets during this phase of the gait cycle, you can get sort of normal levels of walking accuracy or stepping accuracy with only 200 and 250 milliseconds of visibility. So a very short window will still yield full performance. The idea is that if you can see the target during this phase of the gait cycle, that's all the information that you need to basically set up the mechanics of the body, sort of initialize the mechanics of your body, so that the resulting ballistic trajectory of your center of mass will facilitate stepping on the area that you're trying to go to. So simplifying the story a lot, basically the idea is that when humans move through complex environment in places where you need to sort of control where you place your feet, the way that we use visual information is shaped by our sort of implicit understanding of the physical dynamics of our bodies, and basically showing that the biomechanics of bipedal gait shapes the way that we use vision to control our foot placement. So that's sort of a nice general idea, but in those environments there's a lot of sort of questions, right? The environments were artificial. There's not actually a lot of consequences to making a misstep other than the experimenter gets upset with you. I also wasn't looking at all about where people were using their eyes. And so the question is like, how do these sort of results from lab-based studies and these sort of simple observations of the visual control of foot placement help us to understand what's going on when you move through real-world environments where visual information is always available, the ground has sort of this complex 3D structure, and the consequences of a misstep are dramatic. But of course, to study human behavior in this environment is quite difficult, which is why this person's wearing this sort of strange robot suit that you may have noticed earlier. So in order to understand sort of the full complexity of this locomotor behavior in its actual environment requires the use of some complicated technological apparatuses. So for example, the subject that they're walking here is wearing a mobile eye tracker. So this is the scene from that eye tracker. This is a Positive Science mobile eye tracker. He's wearing it behind this sort of infrared face shield. Eye trackers use infrared cameras to track the eyes. Those don't work outside, so you sort of cover it with this IR shield so you can get a nice eye image. He's also wearing a motion shadow IMU-based full-body motion capture system. So traditional motion capture uses cameras to view the person, but obviously you don't want to carry those around outside with you. So these systems use inertial measurement sensors that are strapped to the body to yield a passable measurement of full-body kinematics as people walk over this terrain. So then the question is, how can we relate these patterns of eye movements to the movement that the person made in order to understand how people gather the information that's needed to control foot placement when walking over these kind of rough terrain environments. So to make these things work together, I first had to calibrate the two systems together. I'm not going to get into detail of that, but I'm willing to, if you want to talk about it, I'm happy to talk about that too. But by calibrating the eye tracking data from the sort of video-based reference frame into the three-dimensional reference frame of the motion capture system, you can get this sort of estimate of the full-body kinematics as well as the three-dimensional point of gaze of the person as they walk over this type of environment. So this is being played at full speed. Human behavior is really hard to understand when played at full speed, so I'm going to slow it down a lot. And so with this is being played back at 1/4 speed. And what you can see is that as the person's walking over this type of terrain, their eye movements are sort of doing this sort of complicated dance on the terrain ahead of them, but they're sort of doing something related to these red and blue dots, which show the locations of where the person is going to place their steps in the future. And so it seems that as the person's sort of walking over this terrain, they're doing this sort of mad scramble where they're trying to gather the information that they need to traverse this terrain at the same time that they're walking over the terrain that they looked at several seconds into the future, or several seconds in the past. So it's sort of this strange interplay of trying to build the track while you're walking over it. And so by understanding the relationship between these patterns of gaze on the ground and the motor movements that come up after that, we can get a lot of insight into the way that humans control their behavior when walking over rough terrain and also when moving through the environment in general. For this first part of the talk, I'm going to be talking a lot about how people use gaze to walk over different types of environment. And then from there, I'll move into a look at much more recent developments, which is actually trying to look at the information, the visual information that's used when walking through these kind of terrains. So for this first part, we had people walk over various different types of natural terrains and looked at their gaze behavior. So everything we've seen so far is what we're going to call the rough terrain condition. In this environment, people are walking over these sort of large, sort of boulder-sized rocks. So in these environments, you're kind of walking on the tops of the rocks, placing your feet in a small number of stable locations in the terrain. We also have people walk over what we're calling the medium terrain condition. In this environment, foot placement still required visual control, but the environment was sort of more forgiving. Rather than stepping over the tops of large rocks, you're sort of avoiding a bunch of small rocks. The ground was flatter, And so although foot placement still required visual guidance, it was less constrained than it was in the rough terrain condition. And then of course, we're also going to look at walking in a flat terrain environment. This is kind of a packed earth trail, but not as flat as a carpeted hallway, but more or less free of obstacles, so that a walker in that environment could basically sort of slap their foot down wherever they want and be confident that, that wherever they put their foot will be capable of supporting their body. So one of the nice things about studying walking is that walking is actually a fairly well understood behavior. And one of the things that we know about walking is that when you put someone in an environment, take a sort of standard healthy human, and have them walk in an environment like this, where there's really not a lot of things constraining where you put your feet, humans have a very robust drive to adopt what is called their preferred gait cycle, whereby your preferred gait cycle is the way that you walk in an unconstrained environment, and it minimizes your energetic cost of transport. So all things being equal, if I put you on a treadmill, you will choose the right parameters of your gait cycle that will minimize the energy you expend per unit distance traveled. And in particular, if you look at the combination people select of step length and step duration, you select the right combination of parameters that maximizes your energetic efficiency, the energetic efficiency of your gait. And indeed, in this flat terrain environment shown in green, people show a very, very low variability combination of step duration and step length, and a very sort of tight relationship between those 2 points. And the nice thing about studying walking is I don't actually have to measure their energetic consumption or their oxygen consumption. I can say with a fair amount of confidence that these combinations of parameters for the 6 subjects that I looked at constitutes their preferred gait cycle, constitutes their energetically most optimum way of walking through an environment. So you can compare that to the medium and rough terrain conditions. So that's medium is in orange and purple is medium is orange and rough is in purple. And what you can see is that there's subjects deviate from that preferred gait cycle. Which, again, I can say that because they're deviating from that preferred gait cycle, these changes in locomotor behavior come at an energetic cost. People are walking less efficiently in their environment, in these environments, which presumably is being done in order to place their feet in the limited number of stable, safe locations in those terrains. So the question then becomes, what is it that's driving this deviation from their preferred gait cycle? And specifically, how do people use vision to balance between these conflicting demands? Where on the one hand, you're trying to move as efficiently as possible, and on the other hand, you're trying to maintain stability and place your feet in the locations that are capable of supporting your weight in these different types of environments. So to understand this relationship between gaze and foot placement, it's important to analyze the relationship between these 2 parameters and how that changes in the different terrains people are walking over. So to understand the relationship between gaze and foot placement, did the following text analysis, where to start, you can look at sort of the distribution of gaze along the subject's walking path. Right? So using this representation of the data, you get this intersection between the subject's gaze vector and the ground plane they're walking over. And this shows just one subject walking down that rough terrain. The pink line is the trajectory of their center of mass, and this sort of Gaussian blobs is sort of a density estimate of all their intersections between their gaze and the ground. So to understand how gaze is being used to guide movement, you can then realign all of these gaze-ground intersections with whichever foot was planted at the time that intersection was recorded. So basically, when the person's looking at the ground in this world-centered reference frame, you just subtract the position of whichever foot was planted from the location of that gaze intersection with the ground. And when you do that, you get this sort of distribution of gaze on the ground ahead of them. So basically this 0 point here is where the foot was planted, and you see that on average, when people are looking, their sort of gaze is in this big sort of blobby shape about 1 to 3 step leg lengths ahead of them. And so if you do this for the different terrains, you can see that in this representation, things look kind of similar, right? It's maybe hard to see from the back, but the red triangle here shows the location of the planted foot, wherever the person was when we recorded that gaze point. And then the orange, yellow, green, and cyan triangle show the locations of the step that's coming up. 1 step in the future, 2 steps in the future, 3 steps. And so you can see that in these different terrains, people are generally looking around 2 to 4 steps ahead of them as they walk over the terrain. But we don't, so if we think that people are using gaze to plan their footholds, then we should expect that a large part of the variability of these gaze distributions is going to be correlated with the variability of the steps themselves. So to see how gaze relates to steps that are coming up as a person's walking, rather than subtracting out the position of the foot that was planted when that gaze point was recorded, we can subtract out the position of steps that were coming up in the future. So if you realign, recenter gaze on step n+1, which is the step that's coming up after the current time, you get a change in that distribution. You can also align to step n+2, n+3, and n+4. And what we see when we do that is that that gaze distribution shows a distinct peak when you align to this location of the second upcoming step in the medium and rough terrain conditions, which suggests that despite all the sort of variability in the subject's gaze behavior on the ground, people were generally directing their gaze towards the location where they are going to put their foot 2 steps into the future. So in the medium and rough terrain condition, you can see that feature. In the flat terrain condition, you don't quite see that change shape. So when you realign gaze to upcoming footholds in the flat terrain, this blob sort of shifts down the x-axis, but it doesn't change shape. It doesn't increase its peak at all, suggesting that even though people are looking at the ground, they're not fixating their footholds in a way that they do in the medium and rough terrain conditions. Quantify that a bit by just saying if you just look at the change in the peak of this distribution as a function of which step you're aligning to, in the medium and rough, so again, medium is orange, rough is purple, you can see that peak sort of has a maximum around step n+2, whereas in the flat terrain, there's really not much change in the peak of the distributions. What that shows is that in the medium rough terrain conditions, people are fixating the places that they're going to step, which shows this sort of large correlation between their pattern, their distribution of gaze on the ground, and the upcoming steps, whereas in the flat terrain, people don't really look where they're going to step. And so as a result, their gaze distribution is not correlated with their foot position. So that's nice, right? So that's sort of a nice, so it shows that sort of what we got from the sort of lab-based studies does relate to what we see in in locomotion outdoors, which suggests that subjects' gaze behaviors in different environments are people are deploying gaze in a way that is consistent with a gaze control strategy, which seeks to maximize energetic efficiency when walking through environments where efficient control of locomotion requires gathering information at a particular time in the gaze cycle. However, there's more that we can say about this, right? So this is showing this difference between medium and rough terrain condition where foot placement requires visual control, and the flat terrain where foot placement doesn't require much precise control. But what can we say, if anything, about the differences between the medium terrain and the rough terrain condition, right? Because those are also different. There's a difference in complexity, difference in difficulty, and we want to see if there's some if we can see some hallmarks of that complexity in subject's gaze behavior. So to look at that, we want to ask so more specifically, where are subjects looking and how much people are directing their gaze towards locations of footholds. Because this analysis is actually a measurement of the global gaze distribution on the ground. But as you can see, it doesn't actually tell you where people are actually looking. For example, in the n+1 case here, the peak of that distribution is actually right over the location of step n+2. But they weren't actually looking at n+2 that much. So to get a more specific picture of which steps people were actually looking at in these terrains, we can intend to take the sum of these probability distributions near the origin of each of those step-centered reference frames. So basically taking the sum of distribution inside of these sort of black dotted lines. And what you can see when we do that is that although the medium terrain people are still definitely mostly looking at step n+2, in the rough terrain, people are actually looking somewhat equally between step n+2 and n+3. You can see that here in the medium terrain, that blob is kind of already past the n+3 here. In the rough terrain, people maintain, people will spread their gaze equally between n+2 and n+3. And what we think is that that is coming about because in that very rough terrain, footholds were constrained to the point that you can't just focus on where you're going to put your foot 2 steps in the future. Because if you focus entirely on foot placement, you may find yourself on a trajectory where there is no good step n+3. So although in the medium terrain you're more or less guaranteed to find a place to put your foot, no matter where you chose to walk, which was also true in those lab-based studies, in the rough terrain condition, you need to be sure that whenever you select a step n+2, you're not going to be leaving yourself on a trajectory where there is no good n+3, which suggests that, so basically the implication is that in the rough terrain condition, path planning is something that is a big enough of a constraint that will sort of drive gaze behavior. And that idea is bolstered by a measure of path tortuosity, which is a name that I love, which is a measure of basically how tortuous, how circuitous a subject's path is when they walk. So if you just take the minimum path length between point A and point B, divide it by the actual trajectory the person walked, in the flat and medium terrain, people walk pretty much in a straight line between point A and point B. In the rough terrain condition, people actually follow a much longer path, which suggests that because of those constraints in that environment, people were forced to deviate from that sort of minimum distance path in order to find a place that they can actually put their feet, which is just another way that just shows another one of these trade-offs between the need to move efficiently in sort of this on your preferred gait cycle and the sort of minimum distance path versus the trade-offs that you need to make in order to do those kinds of behaviors in environments where the environment is complex enough that you need to basically make sacrifices to maintain stability in these more complex terrains. So these are sort of, so we see basically 3 distinct patterns of gaze behavior for these 3 different types of terrain, where the way that people deploy their gaze is very sensitive to the specific informational needs of locomotion in those 3 types of environments. And this shows up as well in a more simple analysis if we just sort of ask, how far ahead do people look? So we just ask basically where people are looking on the ground. You take the measurement of how far is that location from the subject's current position. We can see that in the flat terrain condition, which is in green, people are looking a little bit farther down the path, which is also true here. We can also see that people look at the ground less often in the flat terrain condition. But you see, again, the separation between the flat and medium terrains. However, there is a domain in which, despite all these variations, subjects' behavior all looks very similar, and that is time. So if instead of asking how far ahead spatially are people looking, you ask how long will it be until the subject gets to that point that they're walking. In that domain, the flat, medium, and rough terrain conditions all look very similar. So despite all these variations in gaze behavior, subjects are always looking around the place that they're going to get around 1.5 to 2 steps into the future, which suggests that although there are all these despite all these variations in the gaze behavior, subjects are actually maintaining a constant look-ahead strategy. So they're maintaining, so as you walk through the different terrains that have these different constraints, you control your gaze in a way that maintains, that sort of ensures that you will always know what's coming up 1.5 seconds into the future. So just to sort of pin that down, you see that walkers adopt these sort of distinctly different gaze behaviors in these 3 different terrains. And yet, they also maintain a constant look ahead. So putting those 2 things together suggests that walkers are tuning their gaze behavior to the uncertainty of the environment that they're in order to maintain a sort of constant look ahead strategy. Basically, the idea is that when you're walking over this environment, when you're walking through the world in general, the locomotor task actually doesn't change. your goal is always move from point A to point B while moving your feet like this. The difference is that in flat terrain, in simple terrains, doing that task requires relatively little visual information. You can complete that task without really worrying too much about the world around you. You just have to look at the ground every so often in order to ensure that the upcoming path will support your preferred gaze cycle. In the more difficult terrains, getting the information that's needed to place your feet correctly is a much more arduous process. And so as a result, you have to adjust your gaze behavior in order to get the information that's needed to walk over these different types of terrain. So basically, you see that subjects are very sensitive to the different task constraints of these different environments that they're walking over, and you can see these things show up in order to maintain safe and efficient locomotion through these complex worlds. So, 4:30, is that right?
Yeah, we wrapped up 4:30, so.
Cool, yeah, totally. So that's the end of this first half of this talk, and that's sort of, which I think shows a nice way that humans attune their gaze behavior to gather the information that they need to walk over these sort of different types of terrain environments. And so in the time that's remaining, I'm going to sort of very quickly talk about some much newer stuff that I'm working on, much less of a coherent, polished story, trying to get at an understanding of what that information actually is that people are tapping into. So this shows you sort of where people look, but I don't know anything about the actual sort of photons that are sort of guiding those behaviors. So what's coming up next, I'm actually trying to get at sort of doing some sort of video-based analyses of the sort of videos from these attractors to understand what the actual visual information is that's driving the ability to walk through these kind of environments. Like I said, it's all new stuff, much rougher, but happy to show it to you here to show you a sense of where things are going. So specifically what I'm going to start looking at is questions about what's called optic flow, otherwise known as visual motion. So the idea is that the world is often generally quite stationary, so as we move through it, we experience these sort of patterns of motion on our retina that corresponds to our own motion through the world. And there's a lot of study of the way that sort of optic flow, visual self-motion information, contributes to our ability to move efficiently through the world. These ideas have been around for a while, from back in the days of James Gibson in the 50s and 60s. And often the sort of traditional way that it's talked about is with reference to this point right here, which people call the focus of expansion. The idea is that as you move through the world, things will kind of expand outward from a central point, and that point will correspond to the direction of locomotion. And there's a lot of research showing that people are very sensitive to these patterns, so you can estimate your heading relative to a focus of expansion down to 1 to 2 visual degrees, so people are extremely precise in their ability to estimate these locations. And there's a lot of different areas of our brain that are also tuned to these patterns of motion. So area MT and MST are tuned to these patterns of optic flow, and the assumption is from classical literature is that that this information is used to control heading. However, despite 50 years of studying optic flow, nobody's ever actually gone outside and measured it. Not the least reason being that it's actually not really been possible to do that until quite recently. So that's what I'm trying to get into with this next part of the study. So for this part of the study, we're using a different eye tracker. So this is a Pupil Labs mobile eye tracker. It's a nice eye tracker. It's 120 hertz binocular eye cameras, 1080p 30 hertz scene camera, so much better cameras than the previous eye tracker. It's also open source and costs $2,000. It's about a fifth the cost of the other one and a tenth the cost of sort of your standard eye tracker, so that's also nice. And so the idea is just to understand, I can't tell if this video is playing a little faster than this, I'm not sure. So the idea is to try to, using these sort of nicer videos and these nicer eye cameras, trying to understand the actual structure of the visual motion that's coming at the person and how that might be used to control foot placement and to control walking. Also kind of worth pointing out, I think I haven't talked about this yet, look at this sort of crazy stuff that's going on with the eyes when you're walking over this terrain. So this next part, this is all me, these are my eyes. And despite having done this task dozens and dozens of times, I still can't feel my eyes doing all of this crazy stuff. This is being driven at this sort of very low level rate in order to gather the information that's needed to guide this. Is that a hand?
So I probably should have asked our own local expert, but have there been any studies to sort of assess the bias induced by an eye tracker and how you behave? I have differences on that.
I'm sorry?
I'm different from what you show there. So, but if you put an eye tracker on and tell me don't stumble, this is a $20,000 instrument, it will like it very differently. So I guess what kind of bias do you introduce with these instruments?
Well, this is me, and I don't care about breaking these things. So I don't think there's that much of a bias. But I think that you do get differences in behavior when you put an eye tracker on, but only in certain contexts, particularly in sort of social contexts. For this kind of behavior, you put the eye tracker on, it's on a backpack. It's actually, you're not really at a risk of breaking these things when you're doing this behavior, unless you really go down hard, which nobody has done yet. And I think that one of the nice things about this as a task is that it's difficult to the point that there's really not a lot of wiggle room in how you complete the task. Because you're walking over this terrain and you're sort of constrained to walk at this sort of constant speed, you really see very low variability between subjects because the task is difficult enough that there's not a lot of options in the way that you solve it. There's just not a lot of ways to move across rough terrain with sort of two little bipedal feet. And so you don't really see a lot of variations in gauge behavior with this type of task. You do see it in other types of tasks. There's what's called experimenter bias. I'd actually be willing to bet that if you were to find a way to record people walking that flat terrain without having anything on them, you'd see them looking at the ground less often. But in those type of terrains, there's variability. In these type of terrains, there's just not a lot of options in the way that you move your eyes. So we want to understand sort of the actual visual information that's driving these locomotor behaviors, and specifically want to look at optic flow. So to do that, we sort of use the sort of nice, happy plugins from the computer vision community. Thank you all for doing this work for me, so I can just basically give these videos through the far back optical flow estimation algorithm. Fun little quirk of history. Psychologists and neuroscientists call this optic flow. Computer vision people call it optical flow. For a long time, I thought that you guys are saying it wrong, but then when I actually go back and read the original studies from Gibson, he says optical flow. So somehow like the psychology, the neuroscience people changed their terminology, but the computer scientists stayed true to the roots. So there's that. So these algorithms, there's a bunch of them. This is just one of them that sort of is sort of easily available, provides an estimate of the visual motion under each pixel in the video. And so what you can see is sort of this very complex pattern that has a sort of interesting regularity here. So this is a histogram of every pixel's orientation and magnitude per frame. And you can see that there's sort of this interesting sort of bobbing, pulsing shape. And so the question is sort of how can we understand and parse this type of information in a way that is relevant to the control of locomotion, specifically looking at that idea of the focus of expansion and whether or not the actual optic flow patterns match the historical stories of what they're used for, and how can we understand sort of how the structure of this visual information helps us to control our foot placement. So to look at those sort of global structures of these optic flow, we want to start by sort of tracking that focus of expansion. So I didn't really know how to do this, so I actually went and talked to a friend of mine who's a fluid flow engineer and said, how would you, so here's the focus of expansion, right? Clearly it's there. How would you sort of track this point automatically from this scene? And so he says, oh, that actually looks just like sort of a repeller node, right? So it's pushing everything away from itself. So if you're going to track a repeller node, all you got to do is sort of invert that flow field, so just multiply everything by -1, then take a grid of particles and let them sort of flow along that flow field and see where they wind up. So I did that, and the nice thing is first of all, so it works quite well for tracking the focus of expansion. So the place where all those particles wind up is right here, which is sort of right where you sort of visually identify that FOE being. Focus of expansion, FOE, by the way. But the other nice thing that pops out of that is if you track the path of those particles, you can see how they kind of deform and warp around the structure of the scene itself. And that comes out because of what's called motion parallax, where objects that are closer to you when you move will move more than objects that are farther away. So these variations in the visual motion of the scene that is correlated to the 3D structure of the environment. You see people sort of going back and forth like that to confirm that, yes, the heads that are closer to you move more than the heads that are farther down the auditorium. And so what you see is, as people move through, videos are playing slightly faster, but it's actually still pretty chaotic when you play these videos at full speed. So we can slow this down a lot, and we see a couple things popping out, right? So first of all, that focus of expansion is definitely not in a stable location in the visual field. So all those sort of traditional stories of the use of optic flow to control locomotion are very wrong in their assumptions about what optic flow looks like. The other thing we can see is sort of how these sort of flow lines sort of morph and move around the 3D structure of the scene, basically showing this variation that correlates with exactly the kind of geometric information that you would need to control foot placement and locomotion through a complex 3D scene. However, there's sort of another angle to this, which is that this is optic flow relative to the camera on the person's head, which is not actually the pattern of optic flow that hits their eye. So in order to get optic flow in this sort of a retinal coordinate frame, you can do the following thing. So this, I'm just looking at this sort of ball on the ground and moving my head back and forth and up and down. And so in the head-centered frame, you see the eye sort of moving back and forth, up and down accordingly. What you can also do is take every frame from that eye tracker and align it to that point of fixation so that you can get these sort of pixels come back in a reference frame that's centered on the subject's retina. And then, of course, you can recalculate the optic flow and see how things look, the actual patterns of visual motion that hit the back of the subject's eye. Once again, playing this at 1/5 speed, we can see this kind of interesting thing popping up. So first of all, during saccades, which are these sort of fast eye movements, those flow lines kind of decohere because the optic flow algorithms can't track motion at that speed. Humans are also essentially blind during saccades because the image moves too fast. But during fixations, we can see the sort of FOE kind of pops back into view. And it pops back into view roughly around the place the person is looking. And so if we compare this sort of optic flow in this sort of head-centered reference frame to optic flow in this retinal reference frame, we see this interesting feature pop out, which is that in the head-centered reference frame, the FOE and the optic flow in general is actually far more chaotic than it is in the retinal point of view. So if you just compare a couple frames here to there, in the head-centered frame point of view, the focus of expansion is sort of always sort of bobbing and moving around. In the retinal point of view, the focus of expansion is actually sort of centered on the point of fixation, which of course makes sense because when you're fixating something with your eyes, you sort of maintain your eyes pointing at a specific location. You're going to null the image motion at that location. That's what a fixation is. And so by nulling the motion on the things that you're looking at, you basically pull that focus of expansion towards the thing that you look at. Which in addition to sort of changing sort of like big circles to spirals and parallel lines to focus of expansions, will also sort of simplify the optic flow field, which is actually very interesting because if you look at sort of the traditional literature, the story is often how could we recover this nice stable optic flow field in the head-centered reference frame from this sort of corruptive influence of eye movements during locomotion. So these are some studies from some classical studies, basically saying here's this to our traditional story, optic flow in this head-to-head rep frame is sort of this nice, stable, coherent thing that we can use to determine heading. But when you move your eyes, it sort of deforms and corrupts that beautiful motion. And there's actually been a ton of work trying to figure out how we can recover the head-centered optic flow from the retinal optic flow. But when you go back and look at the actual, if you go back and look at the actual optic flow, the actual structure of optic flow during locomotion, we can see the opposite thing is actually true. Where if you look, so this is now looking at the density of that FOE in the head-centered reference frame versus the retinal reference frame. And we see that optic flow is actually much simpler and much more coherent in the retinal frame than it is in the head-centered frame. And so the idea is that by using these new technologies, which are sort of imaging-based technologies, we can actually measure some of these things which haven't previously been available for scientific study. And we can see that sort of a lot of those assumptions that people made were actually incorrect, in that in fact the information that we get from this retinal point of view is far more coherent than the images that optic flow that we get in the head-centered view. Which leads us to sort of another question, which is that traditionally the idea is that optic flow is being used to control heading during locomotion, but who cares about heading? Heading is actually not a hard problem for locomotion. Because we're bipeds, we can start and stop on a dime. We have really precise control over our movements. Heading of some long-term thing is actually a trivially simple problem. We need to do it. We need to control heading, yes, but it's not the hard part of the question. The hard part of the question is determining the 3D structure of the scene around us and determining sort of how the world is geometrically oriented in order to support the actual movements that we make when we walk over these kind of complex terrains and when we walk through complex environments in general. And yeah, that's about it. So, thank you.
We have time for a few questions.
So the focus of expansion tends to be where you're looking. In this case, if you look at this in less demanding tasks, is that still true even if obviously I can find cases where it's not. If I'm walking along and I look off to the left,
Yes.
it's not going to be true.
Yeah, so this is part of sort of where we're trying to parse things out right now, is sort of understanding how much of this is being driven by the fact that you just sort of pretty much forced to look at the ground. What I can say is that so it seems to be that if you're not looking at this sort of the FOE getting sucked towards the point of regard, seems to be a feature of looking at the ground plane. So if you look off into the distance, I don't really have some issues with that, sorry. Looking off in the distance, not fixating, you don't quite get that same behavior because you're not quite nulling that image motion. So this seems to be something which is a feature of fixating the ground plane, which is interesting because basically by sucking that FOE towards the point of regard, you, rather than being looking at these flow lines which are more or less parallel, you're now looking at something where those flow lines sort of sweep out the full orientation sweep, and considering that the motion-sensitive areas of our brain are tuned to those kind of orientations, it's going to increase your sensitivity to the kinds of variations in those optic flow, which are exactly the things that will encode the geometric structure of the environment that you're walking over. So, trying to get it. So those are the kinds of questions that we're trying to get at right now.
So the optic flow vectors are generated from the scene cam.
Yeah.
So the optic flow vectors could be a function of the head motion.
Yes, and they absolutely are.
Yeah, and yes, exactly.
Yeah.
So when we transfer those optic flow vectors to the retinal cortex, it is essentially a representation of the head movement.
When you comparing the optic flow in the retinal frame to the head frame, and the differences between them is basically gives you it's the same amount of information, basically the fixation alignment, like sort of the stabilizing eye moves that we make. Yeah. So basically, when you move and the eyes and the head sort of counter-rotate to maintain stable fixation, that image motion, that difference in those movements basically relate to the image motion that you see there. And you can actually see that in this video, not that one. So if you look at this sort of flow histogram of the head versus the eye, the retinal frame, that flow is sort of smaller magnitude and centered on 0, where in the head you can see this sort of, you can see much more of the head motion in there.
Right.
So
That means, okay, I see. So the optic flow vectors, when they are, so when we make a fixation and when the head is moving, so since then you mix the card, obviously the eye is at a much ahead and the head is lagging behind. So that's why it would be that the optic flow vectors would sort of converge, or the focus of expansion would converge to the fixation point.
Yeah.
And when we transform that to the retinal cortex.
Yeah, and we have there's a lot of sort of neural machinery that's devoted to gaze stabilization, and those stabilizing reflexes basically have always been known to sort of like simplify. Like you can't, your eye just is too slow to see stuff when it's bobbing around at the rate that your head is. But it also has this feature of sort of simplifying these optic flow fields, and by basically nulling the image motion on the fovea, it gives you sort of this more regular optic flow during the motion.
Okay, so here's a weird question for you, but so what you're suggesting is that the biomechanics of the gait cycle, the bobbing of the head because of these biomechanics, structures the optic flow, tells us something about the world.
Mhm.
So it's actually somewhat advantageous for our head to bob while walking, perhaps, right? We're getting more information about the world. So have you thought about the whole chicken and the egg problem? Do you think that we have converged upon our gait cycle because it provides good visual information, or do you think that we have learned to extract this visual information because we've converged upon a very particular gait cycle?
Yeah, I think it's a bootstrapping thing, right? So our gait cycle, it has a lot of mechanical advantages. I mean, a lot of mechanical disadvantages too, but there's nice things about being a biped. But being a biped requires this sort of sensitivity to visual information because you have the planar step cell. All animals have to control locomotion, but we're sort of specifically sensitive to it. So it's kind, yeah. So there are a lot of reflexes. I don't know what the thing is. So the reflexes that we have basically head stabilizing reflexes,
Sure.
And then gaze stabilizing is sort of happening on top of that. So I think there might be something more to the effect of we exploit the consequences of moving in the way that we do as much as we can, basically by the sensitivity to visual motion, while also trying to damp out the hard parts of that. So like, I'm trying to find this thing. I don't know where my mouse cursor is. Oh boy. Yeah, so if you look at the acceleration of the hips versus the chest and the head, during a step, the hips have this massive deceleration, but the chest pitches forward. So the down acceleration plus the up acceleration means that our head is much more stable. In that dimension, but in the vertical dimension, they all kind of roll along for the same ride. So there are these sort of this interesting relationship of stabilizing reflexes in some dimensions, but not in others. And so it's possible that we are tuned to those variations in order to use them efficiently for a gait cycle. It might be a predictive component too, where we sort of say, okay, I'm going to take this step. Here's the flow that I should experience if everything goes well. But if the world starts going like this, that's a cue that I should probably sort of respond to.
Yeah. Time for one more question?
Okay, follow-up question. What conditions would you like for wheelchair users?
Right. So for wheelchair users, right, so there's this very sort of functional level of information I like to think about, which is that the test that you're performing requires certain information to be successful. So when you're legged, leggedly locomoting, you need to be sensitive to certain things and not to others. So when you're in a wheelchair, for example, things like small variations in slant become super task relevant, whereas when you're sort of walking on 2 feet, you can sort of absorb a lot of those variations more easily. And there's a lot of evidence, I mean, looking at the gaze in different terrains and also just some other stuff from Mary's lab and also from Gabe's lab, shows that people are very sensitive to these sort of variations, but very sensitive to information that's task relevant. So my expectation would be that wheelchair users, and particularly skilled wheelchair users, will show an increased sensitivity to these sort of task relevant factors. So whatever those might be, being basically slant and I guess friction in a different sense. And I would expect to see that as you get better and better, even in the wheelchair, you would be more and more tuned to the features that define success and failure for that task. Not going to be exactly what those things are, but that would be my assumption.
All right, we should give John a hearty round of applause. And let me remind everyone that there are cookies and there's coffee out in the lobby if you'd like to ask John